software architecture design or diagram was so you could understand your problem and your proposed solution a bit better. And so you guys have very complex research topics that you're looking at. So it's better, more useful for you guys to be able to describe what's happening using bubbles and so arrows, because they simplify as simple as those concepts or like designs are. They simplify the way we understand our solutions, and so this clarity can be used to more effectively communicate your research. And then it also highlights to you things that you might be able to change, makes you able to modularize and like compartmentalize parts of your program or your software. It also acts as a foundation in which all future development is based on. And so, yeah, those are the main reasons why software architecture are important and important to your research. An example would be TEV2. TEV2s are image generation algorithm. Has a very kind of complex research process under the hood, but using the software architecture diagram, you can see that it's a lot simpler than maybe our articles or some of our other media might suggest it is. For example, a simple search across art platforms is conducted at the beginning. Across these art platforms such as Lexica Art, ArtStation, DeviantArt, Behance, Pinterest, Instagram, and then all these results are aggregated. You can see by the arrows all combining into one bubble. And then from this aggregation of the results, we perform an image analysis collection. And so the results are analyzed for any potential images within the web links. And then within the web links, we can aggregate and understand the image qualities, such as what are the artworks being shown? Is there any artists being referenced? Styles, coloring, textures, that sort of thing. And then from there, we extract the visual elements, like I said, and then we store the data, and that all of this is used to generate subject lines for the image generation process. And so yeah, that's the TEV2. If you're interested, you can obviously check out our website. But this is just an example of how complex processes within AI agents or optimization algorithms can be created and illustrated in a much simpler way through a simple diagram involving some bubbles and some arrows. Also helps you to understand your research, like I said, a lot better, your own solutions a lot better. And so yeah, that is the TEV2. I would like to see some of you guys's diagrams now. So if anyone would like to kind of volunteer to go first and present, it doesn't have to be anything long. It can be a few minutes, just show what your diagram looks like, what is your solution is trying to achieve essentially, and how your diagram kind of displays that. Syed's got his hand up, so I'll let you go first. I'll mute myself as well and stop sharing.
Yeah. Hi. Hello. Hi. How are you?
I'm good. I'm good.
Yeah. Hi, Tammy. Basically, first of all, I'll show you the entire software architecture, and I'll link this with the program as well. For the mathematical details and the kind of the architecture I have designed. I actually need to show how the things works in my whole architecture till now. Just a minute.
So you'd like to show your I didn't catch that. What did you say? Sorry.
I'm saying that I'll share both of the screens together,
Oh, okay.
and not together, but I'll switch from one screen to the another screen in between to actually explain the whole work what I have done in last 4 weeks.
Oh, okay. Yeah, that's fine. That's fine. You don't need to show what you've done in the last 4 weeks. It's just about showing the architecture diagram, like what's happening within within your proposed solution. That's what we're interested in for this week.
So
Yeah,
do you see the screen?
yeah, you can see. I can see.
Yeah, basically, as you know, I'm going to develop the baby AI architecture. I have already done the baby AI architecture in the past. I explained you about the techniques I have used and these kind of stuff. My research objectives are very clear in this research apprenticeship that I'll extract all of the formulas and the equations I have derived during the time of the baby AI, and put this in merge this with the large language models this time to actually give the today's large language models the personality. Actually, I want to give the personality to the large language models, and it is not basically now dependent on the data set, a very big data set. It is very uh, it's kind of an open short learning. Like if you just give him one command, it will learn and reinforce on the same similar patterns. When we say anything to the baby, anything, if we say anything to the baby learn that either it is wrong, it is correct or wrong. The main task of the baby is to learn that, and with the iterations he become accurate and accurate. So my whole architecture is also built on, something like that. I just attach the overall all of the equations with my uh, large language models. So first of all, we got the user input. The user input is in my baby AI, it was the sensory inputs, like the light coming into the camera and the frequencies coming into the ears. But right now we are working with the large language models, so the user input will be the text, always the text. Okay, so once we get the input, automatically the effective update section is opened. And what is this? Basically, it is kind of the feelings I have merged. It's kind of some parameters I have given to the to my baby AI, that whenever some input is coming, your effective update section parameters are open. I have given him the arousal, given him the curiosity, stress, fatigue, and the bonding between the user he's working. And now I know some of the people will question me that how we are going to is this kind of just the variable we are storing some values, or kind of something bigger. So yes, I have read a lot of research papers, collected how basically the arousal work within the human, how the curiosity work within the humans, how the stress increase within the humans. And then I'll I'll collect all of the data and derive the new equations for these kind of stuff. I'm kind of a mathematical boy, so that's why I'm much interested to derive the equations. So I have derived the equations for each and everything, how these works together, and then put this into the effective update. So whenever the user input come, these effective updates will straight away open. On the basis of these effective update that merge with the user input, the dopamine is activated. Dopamine, that is this really is this the input is really matters for now or not. Like sometimes we some like I'm talking to someone, and sometimes I feel that he's not talking something that I love, so my dopamine activation will be very low, not very high. And sometimes I love the topics of the bio-inspired things and the artificial life and these kind of stuff. So whenever someone straight away come to me and say something to me, my curiosity will go higher, my arousal will go higher, my fatigue will go lower, my bonding with that person will go higher. So the dopamine activation is totally based on these all parameters. And once the dopamine activated, it's not all about the dopamine only. It is all about my experience as well. Sometimes we like something, but we forgot that. It is not about something we like. It is about uh, something related we have done in the past as well. Sometime even the thing is bad, but the person we love, the person in front of us is someone who we love. Will love to speak with him. We love that he's speaking about the things. So our dopamine is also increased on the basis of these kind of stuff. So I have derived three kind of a memory structure. One is the user semantic memory, like I am the user. So one is the memory that is solely based on the me, and one is the self model. That means model model also have a memory, also have some affections, also have some things. And the one is the relational memory. What is the relationship between me and the model? So I have divided into a triple memory structure that give the model a personality regards me and the model. And by combining all of this stuff, our workspace, have been learning and the spike time independent plasticity framework, uh, I have already included in the large language model. Instead of the normal large language model, I have uh, placed my Hebbian learning technique and the STDP, spike time independent plasticity, to generate the new text. And the new text will be the output. And on the basis of the output, I reinforce the new parameters into the memory. So this is the overall architecture behind my project right now, not the final one, but till now. This is the architecture, and this is a work I have done. I'll just show you some of my graphics. Timmy, you asked me about what I have basically I have done. So yes, this is the work. You see, hi, what do you know about me? Hello, I see you are curious about something he do not know about me till now. Then very next line, my name is Kumail. His dopamine is something increased, 0.73. His novelty is 0.66. Valence, arousal, curiosity is 0.62. And stress is very down. Fatigue is very down. And these kind of the bonding is right now the bonding is 0.34 only. You will see that the bonding is increase with the time. 0.42, 0.46, 0.49 with the responses. The bonding is increasing with the time. Hi, my name is Kumail. Yeah, nice to meet you, Kumail. How can I help you today with your workspace and consciousness? You are my creation and these kind of stuff. His response, just check his response. He has a tone as well. Tone is warm, curious, with a stubble caution. When if I go and make a 3D model, it will model as well. It will replicate the emotions as well. The emotions are warm, very curious, and these kind of stuff. N- uh, Now with every of the response, he know that I'm Kumail. I love these kind of stuff, and these on basically it started learning from the very first input I have given to him. And the things working in the baby eyes, something like that. You know, the novelty at start was very low. When I say hi, how are you? With the time, the novelty just increase a little bit and then again coming down, because I explain the same thing that my name is Kumail and these kinds. So the novelty will come down. If I explain him the much new and new topics, maybe the novelty will go up. And for the dopamine, for the very first response, see that it is very low. And then I have explained I love these kind of consciousness and these kind of stuff. So it will go, it straight away go high and behave like actually the dopamine is working. And the affective dynamics, arousal, curiosity, stress, it increase with the time, just a little bit, not very much. And this is the personality drift. His openness with me is going is go high. his persistence, like he's first of all he was just something a little bit reserved kind of stuff. Then it is going down because my good bonding is building between me and the model. So the warmth is also go high, the playfulness is a little bit go high with the time, and these are the associations with the time he built in the brain. It's kind of a neural patterns, like in our brain. You see that the neurons fires, and the connection between the it is 0.05, it is 0.05, it is 0.09 with the project and the Kumail, and Kumail and the assistant, it is also 0.09, much higher than these, a little bit higher. And AI and biologically inspired memory, it is 0.08, also higher than these. So basically, the it is kind of an actual architecture of a human learning that I have attached into the large language models right now. This is the work I have done till now. So do you have any question about that?
Oh no, it looks great. It was nice of you to show us some more examples of the outputs and the conversations between you and the baby AI as well. So very interesting. Diagrams is very simple as you can see, guys. So there's not much going on. You can see clearly what's being chained together, the inputs and the outputs, and yeah, I think it helps to better his understanding from what at least what I could gather of his solution, which is baby AI. But so yeah, thank you, Syed. Syed.
Yeah. Thank you.
Um, would anyone like to go next, Joel or Saksham?
I can go next. Yeah.
Sure.
Can you see my screen now?
Yes,
You
but
can.
you don't have
Okay.
anything on it yet.
Okay. Yeah. So basically, this is my structural diagram. This is the entire diagram of all the different components together. And I know that it's a little bit complicated because it's a lot of different things together, but it really plays together into one theme very well. So basically, I have like all these different components, and the problem that I'm trying to solve is that currently we have issues with the multi-agentic systems because if you want to create several multiple AI agents to solve a particular problem in parallel, it is very hard to configure them and make sure that they are collaborating on the same task together instead of drifting apart. And the memory and tokens is also an issue because oftentimes these systems can get into infinite loops, or they can actually have hallucinations that travel from one particular agent to the other agents through contamination by the memory. So I'm trying to solve that problem. So what I have over here is basically the entire system of how my code base works. So initially I have the event generation and storage here, where basically I'm using some APIs from LLMs like Gemini and the Grok API to create a data set. And I'm intentionally using LLM generated output to simulate the LLM results because right now managing the multi-agentic system overhead on top of the system would be too complicated. So I want to work step by step towards the complexity. So initially, I'm just going to create some of these responses, and those responses are simulating what an AI would generally respond in a multi-agentic system as well, because it starts from one system getting a initial prompt. So I'm providing the prompt and then getting the later responses from it. So I'm simulating that data. And after getting that, I'm actually injecting some hallucinations or some mistakes into those because I want to see what happens when these systems make small mistakes and how they can actually multiply and compound inside the system and cause other components to repeat the same issues. So over here, I have the distributed memory layer. That's what I'm currently using. So right now I'm using mock Redis, but otherwise I would be using Redis stream to make sure that the latency is low and that I can quickly exchange the memory as I'm doing these events. This is one of the main components where like my innovation in my research project starts. So I have a task affinity matrix where I have like different roles divided. So let's say for now I'm only thinking about 3 or 4 different roles like researchers, writers, and stuff. So what I can do is assign different keywords or different descriptions to what these roles are, and these can kind of like just serve as prompts So later on, when a particular multi-agentic system is working, and let's say that there is certain conversations happening between the agents and they're generating responses, I want to use these tags and roles that are specified for affinity matrix to understand, like out of maybe more than 100,000 tokens, which of the specific tokens and parts of the conversation that are being recorded are important for this particular task, for this particular agent that's performing the task. And this helps a lot, because otherwise we have a system where we have more than 100 different agents, but each and every agent is basically getting all the information overflooding from the other 99 agents. There's no clear separation of duties and labor between these different agents. I have temporal decay, which is based on like how uh, older the information is. So as we go through the conversation, generally it works in similar to the human memory, where the more recent events that happen around us are more important in our memory, and the ones that are uh, a little bit older, and those that are especially not repeated again and again, the frequency is low, maybe they were only mentioned once, they are not that important, and it's better to give them a lower weightage. This allows us to make sure that the agent's memory is not growing linearly, and that over time it can adjust to very complicated tasks that can run over like several days or months. So this is basically the logic core, where I'm actually coming up with the different formulas, and I have a few examples over here of what the different calculations are that I'm using, like the decay, resonance, stability, and all three combined as a vector of 4 different signals. So that's basically what I'm kind of experimenting with, and this will be calibrated based on more realistic tests that I will keep conducting. So I have like a different if condition here, if the score is greater than threshold or lesser than the threshold. So this is basically an importance score, and this is calculated for different kinds of agents and their roles. So if I get a researcher agent and it actually receives some information which is related to maybe a non-important task, like making some small changes in the markdown file or some kind of small syntax issues, that's not the task of the researcher agents, that's the task of the coder agent that's supposed to do the coding. So it's actually going to give it a low importance score, and it's going to become methylated. Methylated just means is that it's going to stay inside the main memory that we have over here, that we have with the saga pattern as a one causal stream, but it's not going to be visible through that one particular agent for which that memory or that information is redundant. I have some safety gates over here to make sure that the agents do not do irreversible changes that cannot be reversed, like sending an email or sending the money to a different client, so that the verification can happen. And here I have a multi-agentic system of 10 agents, and this system is basically helping me inform the insights for how these systems are going to work, which memory goes to which agent, how they communicate together, and how we are able to make sure that the memory does not increase too much, because research already proves that more than 30% of the context memory of an agent being exceeded causes the hallucinations to increase a lot, and the agent basically starts to forget its memory. So we need to make sure that each one of these particular 10 agents has got the right context and it's able to work very well independently, but still being able to contribute to the main task at hand. I have some validation over here, some A/B testing. So I have like the vanilla implementation where I'm not adding any of these methods, and then I have the Etherflow implementation, that's the one that I'm using, and I have some good metrics, some preliminary metrics for these. So right now I'm seeing like 83.8% cost savings in this scenario, but generally I was seeing at least a 71% cost saving across several tests that I made. So it generally makes things much more cost effective. And I'm also able to see that the amount of memory that's being expressed is lesser now. So we can see that there's only about like 15.3% of the memory that's being used for one particular agent at a time, rather than like 100% of the memory being used, which may not all be useful. And I can see that all these different memories and paths are divided into separate areas. So I can very easily, maybe in the future, click these parts and actually look into what the specific memories are and explainability on why they were excluded. So basically, this is my entire structure where I'm trying to understand how to control and manipulate the memory and the consistency between all these different multi-genetic systems to make them more efficient, more scalable, and more error-free.
Great, Saksham. Very detailed explanation of your solution. My only question would be, where in the diagram, if you could show it again, just briefly.
Yeah, in the diagram.
Yeah, in the diagram. How would you say each of the agents' memory is separated? Like where in the diagram does that
Yeah, yeah.
get
So
displayed?
that's actually one part that I'm currently working on. So for now, basically the test that I have, it's basically just like the 100 events given to me, and I'm actually taking one specific role or two specific roles separately. And what I'm doing is I'm just going to like have the different keywords and tags with me, and I'm going to use that information to see whether this is going to be methylated or not, and I'm doing some review. But what I plan to do over here, like one extra future update I want to make is to have specific summarizations and proper like different hierarchies of memories to be added, because the causal stream itself is very let's say it's very unstructured. So let's say that we have a causal stream over here, and let's say that we have memory number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and let's say that memory 1, 2, and 8 are relevant for researcher 1. So these are actually a little bit scattered around, because it might be that the memories are like just one or two memories from like hundreds of different memories, and they can be somewhat unstructured. So we
Yeah.
need to provide the proper context, and we need to smooth out the rough edges between them, because there might be 100 different events happening between two, but we still need to bridge that gap. So for that, I have some plans with me on how to do it. And I think that's actually going to be similar to how the human brain does it. So this is my future plan in my GitHub repository. So I have the agent query, and then I have like a chapter 1, chapter 2, and like different snapshots.
Yeah.
So maybe after every 10 conversations that happen for one particular agent that I was working, it creates an event, and then it has like different summaries inside, like what actually happened. And then it has a snapshot, which is of maybe 10 events. This is last 3 events, and this is like the current phase. This is compressed from this maybe 10 different events, and then this is like a chapter. And what this helps is that in agentic systems, you can actually very easily hit millions of tokens, and it's so hard to like debug and get the small summarization of like what actually happened in this agent, what were the mistakes that happened, what we learned from these. And if we don't do that, then the mistakes in those agents, those hallucinations are going to repeat again, and we don't have any auditability. So I want to create this system as an extra add-on, rather than like just raw injection of these particular areas into these. So that could work, but I think it wouldn't be ideal.
Oh, okay. Well, yeah, I guess we can talk about that a bit more in our catch-up sessions, but it definitely looks good. Nice diagram. So oh, it would just be you, Joel, next.
Yeah, it's me now. Let me set my screen share. Okay, can everyone see my screen? Yeah.
Yeah.
Cool. So what I'm working on, wait, let me zoom out first. I'm working on a Bayesian prompt compression system, and the problem's pretty simple. It's that LLM prompts cost money per token, and it's quite often that there's unnecessary tokens in there. We can reduce it and retain the same context. So what I'm doing is I'm viewing it as an optimization problem. I'm trying to reduce the the amount of tokens in the prompt, while retaining the quality of the output and the context that it would provide to it. So we start at the input layer, where we've got an original prompt and a prompt made up of components like instructions, examples, and then when it comes to those specific components, there's continuous data for that, like how many examples does it have, how many styling constraints are there, what kind of context has it provided, and there's also the order of the prompts, of the components of the prompt. So like, is it better to have instructions near the beginning, near the end? So we've got 3 types of data there. We've got continuous data, we've got categorical data, and one other type of data. And then once we've got a prompt, I've got a parser. We've got the parsing and encoding layer, so it splits up the prompt into the specific components, what whether it is an instruction, whether it is an example, and then it converts it to a 14-dimensional vector. So from this layer, we get the prompt that's been split up and is now a vector. Separately, what I've done is I've done some empirical analysis on the Big Science P3 dataset, which contains 150 different prompts. And just in terms of analyzing, I wanted to see what is the most important in terms of what components come up most in a prompt, because with Bayesian optimization, the better your prior is, the better your original understanding is, the better your future updates will be. Because with Bayesian optimization, the way it works is it learns the relationship between an input and an output, and then it looks over this search space, this distribution, to find the ideal output, the ideal output ordering and the ideal component, whether the component is there or not. And then from this analysis, I found that, the different importances of each kind of component. So obviously instructions are the most important, then example second most, and looking at style and context, these were the least important. So I use that in my actual optimization process. And then another part of Bayesian optimization is the kernel. The kernel measures the distance between outputs. And standardly, a radial basis function kernel was used, but that's radial basis functions are normally used for continuous data. But as I said in the beginning, we've got 3 different data types. So for the categorical data, whether it did or didn't have a certain component, I used a Hamming kernel. And then for the ordinal data, where it's like the positioning of each component, we used a Kendall-Tau kernel. And then the final kernel is a multiplication of each of the separate kernels. So that's one of the one of the novel contributions to the framework. And then, yes, from, like I was saying before, from the empirical analysis, now that we've got our priors, we can use that to inform our optimization, so that we can inform it, okay, this is kind of the ideal structure. Look in the search space for something that looks like this, but you can also explore different, maybe other structures that have a wider variance than this, but can still perform very well and give us a good mean, because that's the output that you get from Bayesian optimization. So yeah, now that we've got everything, we've got our kernel structure, we've got our informed initialization, we can actually proceed with the Bayesian optimization. And then we loop. For my experiment, I just loop through 20 times, do 20 searches of the search space to find the ideal, the output is an ideal order in vector form. And now that we've got that ideal structure, we can go to actually converting it back from a vector to text, using the prompt builder and text compressor within my repo. So yeah, it removes any unnecessary components, reorders the components based on the output of the optimization, and compresses any text that doesn't carry any context. And I performed some experiments in terms of comparing prompts, of comparing an uncompressed system prompt with the compressed system prompt, and we've got around 30 to 40% compression with an average of 88% semantic similarity of the output. So whether it's compressed or not compressed, we're getting roughly the same output. So yeah, that's my framework.
Nice work, nice work. Yeah, that very detailed diagram. I really like how much explanation you put into each of the steps as well, like explaining the different types of kernels or the empirical analyses you conducted for finding the correct prompt features. That's very nice. This font is very familiar. It's like I've seen it somewhere. Like
it's on Excalibur. I think. Have you used Excalibur before?
I don't think
That's
so.
maybe why. Oh, I can't even tell which one it is. Wait, font family. No, it doesn't even. Doesn't even let me know. Oh, Excalibur font or
Oh, it's
Comic
Dahlia font. Yeah.
Sans.
Oh, okay. Well, I'll definitely be using that font, which is very important to this session. But
Yeah. Okay.
nice work. Nice work. Cool, great. That is I think that's it for showcases of diagrams. So really nice work, everyone. For the last few minutes of this session, because I know this